Hi everyone, this is a short presentation of the new feature in Context 22 open source project for the detection of SQL injection using fuzzy logic. In a previous article on LinkedIn, I have explained why I thought fuzzy logic could be used for such a detection, and it's based on the fact that a SQL injection is the alteration of an existing and valid SQL statement. If we can retrieve that statement, we should be able to infer that there is potentially a SQL injection going on. Such detection can be applied to all types of SQLs and not only on the select, for example, and is also easier to perform in real time when the SQL is received from the Guardium appliance to be uploaded into a data warehouse like Splunk, Sonargy, or Guardium Insight. How does fuzzy logic detect can be used to detect potential SQL injection? And as mentioned, it's because if we consider that a SQL injection is the alteration of an existing SQL, we can compare the SQL we think can be a SQL injection with a set of SQL we know of, and fuzzy logic is able to, by comparing those two statements, to give a score of likeness. And this score is between 0 and 100. And this is what we're going to use. There are two main ways to perform this computation and this check in at least in the Python implementation of fuzzy logic here. One is called standard and the other one is called partial, and it seems that the partial one is more effective at detecting likeness when the alteration is not at the start of the SQL statement or the string of character, and the alteration being down in the SQL statement is more likely what we're gonna have to deal with a SQL injection. So partial computation, I mean likeness, is seems to be a better fit. So let's go to the demo. Okay, so this is an outline of the demo, and we're going to start by 0.0 the environment. It's a Linux environment with a Postgres database, which is a RDBMS database, not a NoSQL database, and in which we're going to record the SQL we want to test against and the score we get by applying the fuzzy logic check, and we do that in Python. Then we are going to start with the basic of fuzzy logic, right? And I prepared here a few tests. So we are using Python 3, and you can see it on Linux. And we have to import this module, and in it we need this one and this one. And we're going to use test first, compare first two SQL statements, this one and this one, right? Using what is called the ratio method. And you can see that the difference is just this question mark. And this, the score is 99, which is expected, I would say. Just to clear up some questions, so it's commutative, right? Meaning that if you inverse, you're going to get the same results, right? So it's really this one and this one are alike at 99%, right? Okay. So here I'm now testing against another one, right? And you can see it's going down, which are a bit surprising because you would expect something because it's very, very similar, right? And ratio here, so that I took something very much closer, and the score is not that great. The reason being that so two things. First, if we do instead of the ratio, which is the standard comparison, and we take the partial one, all of a sudden you see the score is much higher, but it's still not really great. And it's actually because it's case sensitive, right? So even here, when you remove the uppercase, and here I should get something even higher. You see, this is 100% now, right? So therefore, we can say that this one of those two, right, can be considered as SQL injection. This is what I implemented in the module, and in particular, converting all the strings in uppercase in order to make the comparison more valuable, right? First, we're going to create the data structure using this script, and there is two tables in it. The current SQL, the existing one, the reference one, and all the similar SQL we're going to be testing against, right? So it's a one-to-n relationship, and basically those are the two tables, and we've got a foreign key in it, and here a primary key. Actually, we've got a primary key here as well. We're going to see that in more detail later on. Okay, so I'm going to now execute this script. Okay, the problem fixed normally. Exact. Okay, so we got and there is a script to read those stuff, and right now it's empty. So I'm gonna do and you can see actually this is the first table current, and this is the similar one. So it's empty. Then we're gonna initialize this data structure with this script. So here we've got 5 SQLs, and we're gonna upload them into the database. So here and it's done. And if I now read it again, they are here. And let me make it more room. Okay, so you can see the SQL statement, the 5 ones. Okay, and for each one, compute a hash, which is actually here in this case MD5. It's easier to retrieve, right? So I'm not going to use to search for a SQL. I'm not going to use the SQL itself. I'm going to use this hash. So we are now ready to test a few new SQLs against those ones, and we're going to see the results. First, let me show you quickly the 2 Python programs I use here. So let's start with the main. And here the main is actually pretty simple. Okay, it's actually instantiate a module I created, right, which is here, and it instantiates, imports the module and instantiates the class in it, right? But here the point is I don't call the class itself directly. I made it as thread, meaning that it's going to run on its own. This is because later on this module is supposed to be integrated into the enrich ATL. We've got our context 22, and I don't want this process of checking to hold off the ETL itself. It's going to do the fuzzy logic is going to do its stuff on its own separately. Now let's see the module itself, right? Here we've got the fuzzy stuff import we saw before, right? And here I've got a series of the most important functions or method in this case are the opening of the Postgres database, and the check of the fuzzy logic is here, right? So this is, and we use here, we compute the ratio and the partial ratio, but we display both, but we take really only the partial one, right? And then we write into the Postgres database. Then if it's a new SQL statement, the one we are testing, then we record it, because that way it's easier for the management, right? And we need to know that this SQL has existed, right? And here we record all the similar SQL we found. So now let's execute and test one SQL, a new one. So this one doesn't exist, right? So here we go. And you see here that everything worked fine, and it was tested against the 5 SQL into the database, right? And here we've got the standard score, and here the partial one. You see. Okay. Now we're gonna read what we've got into the database. And this is what we've got into the database. Okay, so first, this one has been added. So now we've got 6 instead of 5, right? And for each, so 5, right? For each, and this one was tested against those 5 ones, and those are the results. So for example, here the 070752 is this one, right? So it means that this one was tested against this one, and the result is, the score is 70, right? So this is the second table, the content of second table. So there is a SQL to make it more meaningful. So here it's the meaningful one. Okay, so this SQL tested against that SQL got a score of 70. This SQL, the same one, right? Tested against this SQL, and here the score is using the partial ratio, right? It's 100, right? So this one, and so forth. So we see there is a range of score, right? We are interested in the most like ones, right? So basically we can it can be parameterized, but there is probably no interest at looking at that, right? So probably what is interesting is looking at that or that. So it's why we can restrict the display, and because now those are potential, are candidate for SQL injection, right? So 70 can be considered as a bit low, right? And let's say we consider SQL injection candidate when the score is above 80, let's say. And in this case, we've got only this one. So this is the one that should be sent as an alert to either data analyst or security analyst, right? And saying that this one was executed. It's a new one, and it looks like an existing one. So we can decide, let us know if it's truly a SQL injection, which can be checked different ways. The main one being, is that SQL really a SQL the application knows and has validated? If not, you've got another suspicion of SQL injection. So let's say it comes back and the security analyst or the data analyst have concluded that, yeah, it's a SQL injection. So in this case, what we do is we record the fact to be able to reuse that later on in the real-time process, right? So how we do that, and we're going to change the status, all right? And here we use a hash. It's much simpler. So it's the new one, this one, and the new one, it's this hash. Then we're going to change from pending to SQL injection, right? And the most likely one, right? So this one, we're going to also change it to SQL injection. So that way, we indicate that this one is has been recognized as a SQL injection, and it's an alteration likely of another one, and we know those ones. So now let's do it. Okay, and I'm gonna read it again. And now here, right, this one, the new one, has been flagged as SQL injection. So the one is most like it is this one, and we are interested in the score. And we've got here the list of SQL injection. Okay, so let's see how it looks like on the GitHub repository. So this is it. This is the module. So you can see here the two Guardium, the two Python script, all the SQL, and you should be good to go with that. Okay, so it's among those repository, but for this feature is this one. So let's see quickly the data architecture and the software architecture. So data architecture is quite simple, since as you've seen, right, there is a list of SQL. We're gonna test against any new SQL. The new SQL will be added to that list. So it's a table with a primary key on the hash, and we record with the hash and the hash of the similar SQL. We record those duet, and as much with as well with the status and the score. So the status, as showed during the demo, it's then we flag the SQL as being SQL injection, but we also flag it here to signal to what SQL we think it is as alteration of. In terms of software architecture, it's just one. We don't need much more. It's one module, a Python module containing one class. And the main that PI Python script instantiates the class and runs the object as a thread. The goal is to integrate the check later on into the enrich ETL. And because the idea is really to make this fuzzy logic verification or determination in real time when we receive the SQL from Guardian. Then therefore this module needs to get integrated in the enrich ETL we already have with context 22. Then what are the next steps then in the project? And basically I'm going to try to parameterize the PostgreSQL credential, so that way it's going to be easier. I'm going to make a cloud version. Still the Python, the database will be on the cloud. The Python will still reside on-prem, right? Unless I've found a way to do that entirely on the cloud. But otherwise, I've found out that with GCP in particular, it's good. It's a very good approach to have the database on the cloud, but the process of your data on-prem. And finally, integration with context 22 enrich ETL. Then this conclude this new approach in SQL injection detection with this demo. You can contact us at info. I'm going to put it here. Okay. Info at context22.com. And you can join my my project and the group thread hunting in database traffic I also have on LinkedIn. Thank you very much.